Welcome back, everyone. I am Dr. Flux, and this is General Psychology. We are in Module 6 about sensation and perception. In our last lecture, we took a deep dive into the visual system, how light enters the eye, how the brain processes color and depth, and how vision isn't just about what we see, but it's how the brain constructs a version of reality that's useful enough for us to help navigate the world. But here's the thing, vision is only one piece of the puzzle. It's one of our senses. Today we're going to explore the other senses, the ones that help us hear music, taste our favorite food, feel a soft blanket or sharp pain, and even know where our body is in space without having to look. We'll see how all of these senses work together to create the rich, multisensory world that we experience every day. But before we jump into today's material, let's do a quick check-in from Lecture 6.2. Which pathway of visual processing is impaired in achinotopsia, or motion blindness? Is it A, the thalamic pathway, B, the dorsal pathway, C, the ventral pathway, or D, the occipital pathway? If you said B, the dorsal pathway, you nailed it. That's the where pathway of the visual cortex, and it's where visual motion is processed. Which cones absorb red light? Is it A, S cones, B, Q cones, C, M cones, or D, L cones? The answer here is D, L cones. Those cones are sensitive to light in the range of 564 to 580 nanometers, corresponding to red light. But as important as vision is, it's just one of our senses. Today, we'll explore the rest of the sensory spectrum. We'll hear about audition, how sound waves are transformed into the music and voices that we recognize. We'll dive into olfaction and gustation, how smell and taste combine to create the flavors we love or hate. We'll explore somatosensation, the sense of touch, pain, and temperature. And we'll talk about proprioception, the sixth sense that helps you to know where your body is in space without even looking. Finally, we'll see how all of these senses come together in sensory integration, creating a cohesive and unified experience of the world around us. Then we'll wrap up with some conclusion and review. As we dive into these senses, I want you to keep something in mind. Perception isn't just about what your eyes see, what your ears hear, or what your tongue tastes. It's about how your brain combines all of these inputs into a single, coherent model. And as always, remember our guiding idea: all models are wrong, but some are useful. Your sensory systems don't give you a perfect picture of the world, but together, they create a model that's good enough for you to survive and thrive in your own environment. So let's get started. First up, audition, or hearing. From the rhythm of your favorite song to the subtle tone shifts in a conversation, sound is a powerful way we experience the world. But how does your brain turn simple vibrations in the air into meaningful experiences like music, language, and maybe even impact your emotions? Let's take a closer listen. Here's how that transformation occurs. First, the outer ear collects sound waves and funnels them through the auditory canal. Those waves then hit the eardrum, making it vibrate like the skin of a drum. The vibrations are passed through three tiny bones in the middle ear: the hammer, anvil, and stirrup. These amplify the sound signal. Finally, the vibrations reach the cochlea, a spiral-shaped structure in the inner ear filled with fluid. Inside the cochlea, tiny hairs move depending on the frequency of the vibration. It then converts those vibrations into a neural signal that your brain can understand. It's like turning air into electricity, and then that electricity into meaning. So how does your brain tell the difference between a high note and a low note, or a whisper and a shout? Pitch is all about the frequency of sound waves. The faster the waves vibrate, the higher the pitch. Think of a whistle. It's high-pitched because it's a high frequency. Slower waves create lower pitches, like the rumble of a drum. Volume, on the other hand, comes from the amplitude of the waves. The bigger the wave, the louder the noise. Now here's a cool trick that your brain does without you even realizing it: sound localization. Your brain figures out where a sound is coming from using binaural cues. That just means that it compares what each ear is hearing. The interaural time difference is the time delay between when a sound reaches one ear and when it reaches the other. If someone's calling your name from the right, the sound will hit your right ear just a fraction of a second before your left. The The interaural intensity difference is about volume. The sound will be a little louder in the ear that's closer to the source. Your brain uses these subtle differences to create a 3D audio map of your environment, helping you to figure out where a sound is coming from. Once this sound signal reaches your brain, it's processed in the auditory cortex, which is located in the temporal lobe. This is where things get a bit interesting. Your brain doesn't just detect sound, it interprets it. For most people, the left hemisphere is where language is processed, and the right hemisphere is more involved in processing of music and emotional tones and voices. That's why hearing someone's tone can tell you just as much as their words. It's not just about what they're saying, it's also how they're saying it. And our brain interprets both of those pieces of information. Now that we've tuned into how we hear the world, let's switch gears and talk about how we experience the world through smell and taste. These are our chemical senses. They detect molecules in the air and on our tongue to create sensations that are deeply personal and emotionally powerful. Let's see how these sensory systems work, starting with olfaction, or the sense of smell. When you breathe in, airborne molecules enter the nasal cavity, and they bind to specialized olfactory receptors. These receptors send signals to the olfactory bulb, which sits right at the base of your brain. And here's where it gets interesting. The olfactory bulb has direct connections to the amygdala, which processes emotions, and the hippocampus, which is responsible for memory. That's why a simple smell, like freshly baked cookies or cut grass, can instantly transport you back to a specific time and place in your life. Smell is one of the fastest ways to trigger a memory. Now let's talk about gustation, or the sense of taste. Your tongue is covered in taste buds, which detect dissolved molecules in the food that you eat. These taste buds are sensitive to 5 basic senses: sweet, sour, salty, bitter, and umami. And umami is the rich, savory flavor that you find in things like soy sauce, Parmesan cheese, and meat. Let's reflect. Have you ever caught a whiff of something? Maybe the smell of rain on the pavement or a specific perfume, and been transported back to a vivid memory. Or maybe you've had a meal that brought you right back to feelings of togetherness or some memories from your childhood. These experiences show us just how deeply smell and taste are connected to our memories and emotions. It's about how your brain ties those sensations to the stories of your life. So far, we've explored how we experience the world through sound, smell, and taste. But let's shift to something even more fundamental: touch. Your sense of touch doesn't just help you feel the softness of a blanket or the heat of a cup of coffee. It's how we detect pain, sense temperature changes, and even understand where our body is in space without having to look. This is somatosensation, the sense that keeps you grounded in your body and connected to the world around you. Somatosensation might be a fancy term for your sense of touch, but it includes pressure, it includes temperature, it includes sensing pain, and it also senses vibration. Somatosensation also includes proprioception, your sense of where your body is in space. Your skin is packed with specialized receptors that help you to make sense of the physical world. Mechanoreceptors respond to pressure and texture. They help you feel the difference between the smooth surfaces of a glass and the rough textures of sandpaper. Thermoreceptors detect temperature changes. They're why you feel refreshing chill of an ice cube or the comfortable warmth on a sunny day. Nociceptors are the pain detectors. They signal when you're touching something that might be dangerous, whether it's a sharp object, extreme heat, or pain from an injury. These receptors send signals to your brain, helping you to react to your environment, protect yourself from harm, and experience the world in a tactile way. Once your skin detects a sensation, the signal travels to the somatosensory cortex in your parietal lobe. This part of your brain is like a map of your body, and it's referred to as the somatosensory homunculus, or little man. The cool part is that this isn't a proportional map. Areas of your body with more touch sensitivity, like your fingers, lips, and face, actually take up more space in the brain. Less sensitive areas, like your back, take up less space. This is why you can feel even the tiniest speck on your fingertips, but might not notice a larger object brushing against your back. Let's do a quick attention check. Which part of the brain processes touch signals from the body? Is it A, the occipital lobe, B, the temporal lobe, C, the somatosensory cortex, or D, the frontal lobe? If you picked C, somatosensory cortex, you're right. This part of the parietal lobe is where your brain maps out all of the touch sensations from your body. Now let's talk about a related sense. I also think it's rather underrated. Proprioception. Proprioception is your brain's ability to know where your body is in space without having to look. It's how you can touch your nose with your eyes closed, walk without staring at your feet, or even type on a keyboard without looking at your hands. Your muscles and joints are packed with receptors that constantly send signals to your brain about the position and movement of your limbs. It's like a GPS system for your body. So how does this proprioceptive system allow us to stay balanced? That's where the vestibular system comes in. It's your body's internal gyroscope, helping you to stay oriented and balanced even when the world around you is shifting. The vestibular system lives in your inner ear, and it's responsible for detecting the position of your head, the movement of your body, and helping you to maintain your balance. The vestibular system has two major components. This includes the semicircular canals, which detect rotational movements. Imagine spinning in a chair or shaking your head no. These movements are picked up by the fluid in those canals, which shifts to tell your brain that you're rotating. The otolith organs, the utricle and the saccule, detect linear movements and the pull of gravity. Think about riding in an elevator. When it suddenly starts moving up or down, your otolith organs let you know what's happening. They also detect when you tilt your head forward or backward. Together, these structures send signals to your brainstem and cerebellum to help you adjust your posture and maintain balance. But the vestibular system doesn't work in isolation. It teams up with other senses to create a stable experience of the world. It uses vision for the cues that help us understand our surroundings, like seeing the horizon when you're on a beach or focusing on a fixed point when you're spinning. Proprioception gives feedback from your muscles and joints, helping you to understand where your limbs are without looking, and then somatosensation lets you feel the ground beneath your feet or the sensation of leaning against a wall. When all these systems work together, you stay balanced and oriented. When they don't, well, things can get a little messy. Have you ever felt nauseous while riding in a car or dizzy after a boat ride? That's motion sickness, and it happens when your sensory system sends conflicting messages to your brain. It's when your inner ear is telling your brain that you're moving, but your eyes, focused on a stationary book or a phone, are saying that you're still. This mismatch confuses the brain and results in awful feelings of nausea, dizziness, and disorientation. So we've talked about these senses somewhat in isolation, though I have been talking about how they come together. And that's really important because we don't experience the world one sense at a time. Our brain is constantly integrating information from multiple senses to create a single coherent experience. And when these signals are in conflict, your brain sometimes makes wild guesses about what's going on. So let's take a look more specifically at how our senses work together to build perception. Multisensory integration. Think about eating. Our sense of taste and our sense of smell combine to form an experience that is larger than the sum of its parts. This is known as flavor. The experience of flavor is a combination of taste from your tongue, smell from your nose, texture and temperature from tongue receptors in your mouth, and visual cues about what we're looking at. For example, studies have shown that people often perceive red drinks as sweeter than clear ones, even when they're identical in taste. By combining all these inputs, the brain creates a richer and more accurate understanding of the world around us. But sometimes it can go wrong. Sometimes cues from one sense might influence our perception a bit too much. One of the most famous examples of this is the McGurk effect. Let's watch a video to understand this.
Ba, ba, ba.
Have a look at this. What do you hear?
Ba, ba, ba. Ba, ba, ba.
But look what happens when we change the picture.
Ba, ba, ba. Ba, ba, ba. Ba.
And yet, the sound hasn't changed. In every clip, you are only ever hearing ba with a B.
Ba, ba. Ba.
It's an illusion known as the McGurk effect.
Ba.
Take another look.
Ba.
Concentrate first on the right of the screen.
Ba.
Now to the left of the screen.
Ba.
The illusion occurs because what you are seeing clashes with what you are hearing.
In the illusion, what we see overrides what we hear. So the mouth movements we see as we look at a face can actually influence what we believe we're hearing. If we close our eyes, we actually hear the sound as it is. If we open our eyes, we actually see how the mouth movements can influence what we're hearing.
Let's unpack what just happened. When you watch a video of someone saying ba, but the visuals make it look like fa, you hear fa instead. Even though your ears are hearing one thing, your eyes are telling you a different story, and your brain is trying to reconcile the two pieces of information. It's a fascinating example of how your brain isn't just passively receiving information, it's actively trying to make sense of the world, even if it has to invent a bit of perception to do it. Now let's talk about something even stranger: synesthesia. Synesthesia is when stimulating one sense automatically triggers a response from another. For example, some people see colors when they hear music. Others might associate specific numbers or letters with colors. For example, the number 4 might always be associated with blue, while the letter A might feel inherently red. This isn't something that people are imagining, it's how their brain is processing this information. And synesthesia shows us that the boundaries between our senses aren't always as rigid as we might think. Another example of sensory integration that sometimes isn't very helpful could be seen in phantom limb sensations. After an amputation, people often still feel sensations, sometimes even pain, in a limb that doesn't exist. This happens because the brain still has an internal model of the body, but it hasn't been updated to what's actually occurred. It's a powerful reminder that perception isn't just about what's there. It can be about how the brain constructs reality based off of our prior experiences. We've taken a deep dive into how we experience the world through our senses. From the vibrations we hear, to the flavors we experience, to the textures we feel, and the balance that keeps us upright. Each of these systems plays a role in how we perceive and navigate the world, but the real magic happens when all of these senses come together. Your brain isn't just receiving information, it's actively constructing your experience, integrating sensory inputs to build a model of reality that's useful enough to help you thrive. Let's review. Audition allows us to hear and interpret sounds, from spoken word to the rhythm of our favorite music. Smell and taste are chemical senses combined to create flavor, but they're also deeply connected to memories and emotions. Touch helps us to feel the world around us, while proprioception and the vestibular system keeps us aware of our body and balanced in space. But we don't experience these senses in isolation. Multisensory integration allows us to merge this information together into a coherent experience. And that is the heart of all of this. Perception isn't just about what's out there. It's about how your brain constructs a version of reality that helps you to make sense of your world. Before we wrap up, here's a couple of review questions. Which structure in the ear transforms sound vibrations into neural signals? Is it A, the eardrum, B, the cochlea, C, the hammer, or D, the auditory canal? The answer here is B, the cochlea. The cochlea converts vibrations into neural signals that your brain can interpret. Which condition is not associated with altered multisensory integration? Is it A, the McGurk effect, B, synesthesia, C, phantom limb syndrome, or D, congenital analgesia? If you picked D, you're right. We haven't discussed congenital analgesia in this lecture, but it refers to the genetic loss of the ability to feel pain. As we close out this module, I want you to remember, perception isn't static. It's an active, dynamic process where your brain is constantly interpreting, adjusting, and constructing a version of reality that helps you navigate the world. Sometimes that model is flawed. We've seen how illusions, motion sickness, and sensory conflicts can trick us. But even when it's not perfect, it still can be useful. And that brings us back to our guiding idea: all models are wrong, but some are useful. Your perception of the world is a model, one that helps you move through life, connects with others, and makes sense of your experiences. Thanks for joining me on this whirlwind tour through sensation and perception. Remember, stay curious, stay resilient, and above all, live life in flux. I'll see you in the next module.